Welcome everyone to this new Gravity class session. This is the second of the semester. The speaker today is Sebastián Olivares. He did his undergraduate and master's degree in Pontificia Universidad Católica de Chile. He got his PhD on experimental particle physics at the University of Edinburgh in UK. He also did a postdoc at Pontificia Universidad Católica de Chile, and now he's a professor in Universidad de Tarapacá. His main interests are in data analysis, focus in Higgs physics and implementing machine learning algorithms in data analysis using the Atlas detector data of the LHC. The title of the talk is Machine Learning Evolution at the LHC. So Seba, thank you very much for giving this talk, and please go ahead.
Great. So I'm going to turn off the camera just to focus on the slides. So yes, I'm sorry, Francisca, for changing the title, but it's the same thing. It's evolution or introduction to machine learning at the LHC. And as a content, I put there, like I didn't put the whole names, but I'm going to talk first about the LHC, a little bit of how it's related with machine learning. Then multivariate analysis, which is how we call in particle physics any machine learning analysis. Then I will go to the first one that we used like long time ago, was boosted decision tree, BDT. And then I'm going to give a brief explanation of what is a neural network, because it's what we are currently doing now at LHC. Then deep neural network, I'm going to talk about a specific deep neural network that's called the convoluted neural network. And at the end, I'm going to briefly talk about the transformer neural network. So, okay, there. So how we do analysis at the LHC, or how we do like an analysis in particle physics or in collider in general. So we can move a little bit back to go to the simplest detector that we used to have before. So these were some of these were the bubble chambers, which is kind of like a cloud chamber, which is a chamber that is filled with superheated liquids and these boils, and then when a particle passes through this liquid, it will leave a path. So from the path, you can take into account where the particle was, and also you can take into account the momentum from the curvature of the path. You can see there. These were photographed and then were analyzed each event individually. So the question would be like, okay, so this was before, like with the bubble chambers of the 60s. So how complex are the current particle detectors? So at LHC, there's one detector that's called LHCb, which is focused on physics. And if we compare this one with bubble chambers, we can say that in every 6 seconds of this detector, it's the same thing as, or we can record the same information as the big European bubble chamber in its entire life, which was 11 years of operation. So it's a huge difference. This is because right now we're living in the big data area, not just in physics, but in general. We have a lot of data to process, so we cannot use the same method that we used before. So then I'm going to give you some facts about the LHC. So the LHC data rate is like 1 petabyte per second. The Higgs boson is produced only once every a few billion proton-proton collisions. This is why we need to have this big amount of data, because we have some processes that they are like really unfrequent, so it's really complicated to produce as the Higgs boson. And then if we focus in 2 other experiments at the LHC, which are Atlas and CMS, each one of these has 100 million detection elements. So we compare with the bubble chamber. The bubble chamber has just 1 detection element, because this other one has 100 million, so it has much more information. And then it's impossible data. So Atlas and CMS, they do a data reduction of the data, which we call trigger. And at the end, we can have 50 terabytes per second when we have this reduction. So it's a big reduction, but still there's a lot of information. So how much information I have been putting you some numbers, but we can compare with something. So if we compare with Facebook, we can store as much data every hour in Atlas or in CMS as what Facebook collects globally in a year. So you can see it's a big difference of data. So we can ask to an expert, which is Geoffrey Hinton, who is one of the fathers of deep neural network. We can ask him and tell him, okay, we have all this big data. The idea is to reduce it and try to extract the needed or the data that we need to do an analysis. So he will tell us, oh yes, like let's use machine learning because machine learning excels in the collection and analysis of big data samples, and then you can have like good information from this. So he will probably tell us that bring it on and let's begin analysis together. But there are some difference between the normal machine learning or the normal issues that machine learning face with what we can face at the LHC. So this is like a brief explanation, maybe for the people that are not in physics, which I believe no one of us is like this, but let's go with it. So the first thing that we have, the difference that we have between particle physics or the LHC physics with what the common machine learning issues are, is the first one is that particle physics is governed by quantum mechanics. So let's put here an example of what we can do with a machine learning algorithm to differentiate a cat from a dog. So what we do is that we give different label picture of a cat of a dog to a machine learning algorithm, and this one gives us an output what it distinguishes. So let's say that we give them a cat, and at the end the output will be a cat, so it will be correct. The issue with quantum mechanics is that sometimes, not sometimes, but the input parameters are not a fixed value, an integer of a cat or a dog, but it's a probability of having a cat, it's a probability of having a dog, and sometimes you can have something in the middle. So you can have a phase space of having a cat and a dog at the same time. So this is from the Schrödinger equation. So you can have a probability of having a cat or a dead cat at the same time. So what the LHC does is the same thing. So at the LHC you have a collision of two protons, and from this collision you can have different kind of events. So let's say that we want to distinguish a Higgs event from all the standard model background. So the Higgs is this one over here on the left, and the other standard model background is what you have on the right. So if you want to distinguish this one, it's not as easy as distinguish a cat from a dog, because you're going to have a probability of producing this one and also a probability of producing that one. And what is even worse is that you're going to have also interference between these two. So you have a state where you can have a Higgs or a standard model background at the same time. So let's put this in equations. So you're going to have a probability function of having a matrix element of a signal, which is going to be our Higgs, a background, which is going to be all the standard model background. And you can, let's say that you are doing analysis and you want to take some like specific cases. So we can have a specific case where most of the events are going to be signal. So we can say that it's going to be a signal event. Let's say, for example, in the case of the Higgs boson, if we focus in a specific invariant mass close to 100 to 125, then we're going to have more signal events than background events. And we can also do the same thing for the background. So we can do the same thing, and then let's take into account the same example about the invariant mass, and we go like further up in the invariant mass, let's say to 1 TeV, and then in 1 TeV we're going to have mostly background events and not signal events. So then we're going to have a probability of all the data that is going to depend on the probability density function of the signal and the background, and it's going to be multiplied by this possibility of having a signal or a background event. At the end, the probability of like the sum of both probabilities are going to be equals to 1. So we understand now this, but there's something else. Okay, there's something else that particle physics or LHC physics differ from what we have on the other machine learning problems, is that how like the simulated data that we have, the Monte Carlos are really accurate. So let's take some facts again. So the LHC was created at the beginning to prove physics at the order of 10 to the minus 18 meters. Let's compare with something, the Higgs boson size supposed to be 10 to the minus 17 meters. So then first, like how we model all these between 10 to the minus 18 to the minus 15, we have a semi-classical Markov model that turns primordial particles into hundreds of quarkus gluons. These quarkus gluons, then they got together. And then between 10 to the minus 15 to 10 to the minus 6, we have the quartz gluon that turns into metastable subatomic particles as jets. And then at the end, the detectors as ATLAS and CMS or LHCb, they are accurate between 10 to the minus 6 to the 100 meters. We're not detecting the Higgs boson directly, but we are detecting how it decays. But still, the Monte Carlo that takes into account all these simulation from like check the pointer that I have here, right? So it's from the first collision to having the first particle, and then when this particle hadronize, and then to form into jets. All this precision is really high, and it's not something that you can see in any other field of machine learning. So then, how we process all this data. So what we had at the beginning, we have we process all these raw data and we transform this into a low-level objects. Let's say, for example, that we have some activity in the calorimeters, and then we organize this activity in a cluster. And from all these clusters, we can reconstruct a track of this particle. Then we can estimate the energy and the momentum of this particle. We identify this individual particle. And then we can do several selections. Let's say, for example, that we want to know the position of this particle. So we will just take into account the particle that is in a certain position. Let's say the forward position. So we can make a further analysis. We can then make further cuts. And with all this, we are reducing the dimension of this Monte Carlo, which is very good because after reducing this dimension, we can run our codes and we can have like some sensible information. It's very important to reduce the dimension because it won't be possible for any computer to take the raw data and make analysis over this. So now that we know like a decision between machine learning algorithm to what we can have at the LHC, I'm going to explain a little bit of how we can reduce this information. So I'm going to take, for example, again, the Higgs. So this is a specific analysis of the Higgs, that is the Higgs when it decays to a pair of Z boson. And then after this, Z boson will decay to a pair of leptons. So this is called the Higgs to 4 lepton because the final state of the analysis are going to be 4 leptons. So this process is really rare. It occurs just once every few billion proton-proton collisions. So we need a lot of data to see this process. So here in the left, you can see kind of like a Phylum diagram of the Higgs and then the 4 leptons. And each one of these leptons will have a specific energy, momentum, and another characteristic. So a good way to reduce the data of this analysis and to distinguish also the Higgs boson from the background would be to use a specific variable that is the invariant mass that I took a little bit before. So this is how you calculate the invariant mass. And this is the picture of the invariant mass. So in like light blue, you see the Higgs Monte Carlo. So this is how the Higgs will look like. And then of the invariant mass of the Higgs. And then you have the invariant mass of the background. So notice like as first eye that it will be a good way to reduce the background, to distinguish your signal from the background, to use just this variable. You can focus just on this part. So the typical question after this is like, okay, you did this analysis, you got good result, but is this the optimal way to to do this analysis. So we can do it in another way that you can have even better results. So yes, of course, there's another way. So the other way is to don't use just the invariant mass of the Higgs boson or of the final state particles, but to also use other characteristics. Let's say, for example, that we can use also the invariant mass of the two set bosons. We can use also the decay angles, the production angles, and many variables. This is what we call multivariate analysis of using many variables. And this is something that in any other field besides particle physics, everybody calls machine learning. So this is in the plot that you can see here is maybe the first type of machine learning that we use at the LHC, which is using the matrix elements. So you're using all these angles and invariant masses. You run them together in a variable, and you distinguish your signal from your background. But then after this, Atlas and CMS and also the LHCb, maybe from the 2010 or something like that, like close to that era, the status quo of any HEP analysis was to use boosted decision tree, which is a specific learning algorithm. And we use it with a software or a package that was already part of our normal package that was root. So it was really easy to use it, which is called TMBA. So how does it work? So it's worked as a decision tree. So what is a decision tree? You're gonna have a question. So let's say that you're gonna have a particle that you don't know what it is. So this particle, the first question that you're gonna ask if this particle is charged or not. Let's say, for example, that you would like to have at the end an electron. So you want it to, if it's charged or not. If it's not, then you are gonna decline the offer. And then if it's yes, then it's gonna go to the next step. Next step, okay, you want to have an electron. You don't want it to have a big mass. Okay, how big is your mass? Okay, it's 1 TeV. Okay, no, you're not an electron. Then you go to the next step until the end, you're gonna have an electron. So you're gonna accept the offer after your last selection cut. Decision nodes are the question that I did. So if it has a momentum, charge, and all that. And the leaf nodes are gonna be what you have at the end. So you're gonna have sometimes you decline the offer if it's charged or not, if it has 1 TeV or not. But sometimes, let's say it's not gonna have 1 TeV, but it's gonna have 1 GeV. Maybe your detector was not good enough, so maybe that one is an electron or not. So these one are still leaf nodes because you can still work on these nodes. Same thing that you can see over here. So you have your decision node, your leaf nodes. This is like a decision tree, but things are a bit more complex because these are called boosted decision trees. So in boosted decision trees, you're gonna have not just one tree, but you're gonna have multiple trees. You're gonna have your safe data, like if you see an electron, let's say which has, this is gonna be your safe data, your input data. Each one of these trees is gonna have an output. So if you have an electron or not, how probable is this electron is going to be electron or not, then you're going to have a weight. So this is a little bit more complicated. So you're going to have an output for each one of these trees. And then the output of all this ensemble, so the group of all these trees, is going to be given by this function. So you're going to have the output is going to be a weight that is multiplied by the tree output. So what is this weight? This weight, the final idea of all this is to have a result, and that this result will differ as little as possible with the truth value. So your prediction has to differ the smallest possible with the truth value. So you do this several times. You identify which one of these decision trees is the most important one. How you identify this? By having the smallest error. So when you have the smallest error, you're gonna give something more important to some decision trees and not to the other decision trees. And then when you do this, you're gonna have like your optimal result. So I talk about, so the idea is to have the smallest error when you compare your prediction with the truth information, but I didn't tell you where you can have this truth information. So the typical thing that you do when you have a machine learning problem is that you divide your data, your input data, you divide it by your test data, the one that you're gonna test data, and also the training data, the data you're gonna give to the model. Let's say, for example, that you want to distinguish different geometric figures, a triangle, an hexagon, or a square. And then you're gonna have your testing data that you know which one is gonna be a triangle, you know which one is gonna be your square or your hexagon. But then you divide this data, as I told you before, and you give some of this data to the training, the model training. This BDT or any machine learning algorithm will not know which data it has as an input, but it's going to give you a prediction. And then it's going to be a prediction that it's going to be, let's say, a square. And then you're going to compare with your testing data, and you're going to say, okay, I told you that I gave you as an input a square, you got me as an output a square, then you got a good prediction. But sometimes it won't have a good prediction. And that's when you work around with this machine learning algorithm. So using just BDT for the first years, in this case, I put some examples of how good was LHCb at the beginning. So in the case of LHCb, there was a dark matter searches that used BDT using just data collected in 2016. And if you didn't use BDT in this analysis, it would have required 10 years instead of just 1 if you were not using BDT. So it tells you the big power that BDT had on this analysis. Also, BDT was used on CMS to increase the resolution of the electromagnetic calorimeter, which is the plot that you can see here. So the idea is to have this is a set boson. You have the width of the set boson, and the idea is to have the smallest width as possible. So the red one is just the raw information that you can have. The green one is like with a common analysis without using BDT. And the blue one is the one that has BDT. So the set boson is well centered with the BDT analysis, and also the width is much narrow. So this also tells you that how you increase the resolution using BDT. And then this is an example of this is all the Higgs analysis that we got with, not all, but some Higgs analysis that we got with ATAS and CMS with different final states. This plot tells you how much data we will need if we were not using BDT to have the result that we got from this, so to have the discovery. So we have from 51% of more data that we needed if we didn't use BDT to 125% more data that we needed if we didn't have BDT. So I'm going to move to another topic. So particle physics has traditionally been using physical motivated classifier. The input that we give to BDT are momentums, invariant masses, angles, and all of these are, for us, they are physically motivated because we understand it quite well. But over the last several years, it has been replaced by modern machine learning. So the modern approach is to feed raw, so minimal processed data, rather than high-level physical motivated variables. So as I told you before, we have this is the same slide that I showed before of the steps that we need to do to reduce the data. So the first point was to use raw data, but then it was to reconstruct a particle. But now with machine learning, the idea is to don't do this, as the cats say, but to try and let the machine learning algorithm to reduce data. So this is just an example of how we can improve the analysis using machine learning. So in the case of BMS analysis, the CMS and LCB, they were the first to identify an evidence of this decay. They did it with a BDT, so a human design tracking algorithm was first reconstructed, the paths of these muons and anti-muons. And then from these paths, they could reconstruct the momentum of the particles, and then they infer the momentum of the particles. And then they use just two variables, that was the dimuon mass, the Meyer mass, and also the angles that were used with the BDT. So our question, or what I mentioned then, is that the information can be lost when these human design tools are used, because we are, as I say, we are like reducing the information. And what if we reduce information that were really useful? So this is what we want to do with raw event information of a machine learning algorithm. And this is one of the modern machine learning algorithms that are really good with this raw information as input, are neural networks. So I'm going to explain a little bit more basically what is a neural network. So a neural network is same thing as we mentioned before BPDT. I'm going to give more time for this explanation. So you're going to have different input parameters. These are the x1, x2, and x3 you can see on the left. And these input parameters, you give it to a neuron. And this neuron does a function, so it does an algorithm inside that will give you an output, and the output will be the output of your machine learning algorithm. But what it does inside, so inside you're going to have, again, something pretty similar to what you had from the BDT. You're going to have a set of weight, and this one are going to be multiplied by your input parameters. So you see there, so each input parameter will have a specific weight. Which weight should you use for each one is what the machine learning algorithm will decide. It will decide because of what parameter it thinks that is going to be the most efficient to have a result with the less error as possible. So something else that machine learning does is that it's not that it will give you a linear answer or a linear result of your error, but it will be a not linear function. And how you not linearize your final result is by using an activation function, which at the end will tell you which neuron is going to be activated or not. So I just mentioned to do it with just one neuron, but you can use several neurons that are tied together. And this is called deep neural networks. So you're going to have several neurons tied together, and then you're going to have several layers of neurons that are tied together. So it's what you can see like over here. Let's say that you, again, you're going to, the idea is to try to recognize different geometrical shapes. So you have a square, a circle, and a triangle. You're going to have an input layer. It's going to be the one that is going to give you the information. Some hidden layers that are going to be the one that are doing the hidden or all the work that is going to distinguish between a square, a circle, and a triangle. And at the end, you're going to have your output layers. It's going to be the final result. So the idea of this is the same thing as what we mentioned before. So you're going to have these layers are going to be connected by, let's say, some lines. And these lines are going to have also a weight. So each input variable, we're going to have a weight. And the neurons that are like yellows are the ones that are active or not. Which ones are active or not? The ones that are useful. How we know it's useful or not? The activation function that I mentioned before. And then you move from one layer, and then you go to the result of this one will go to the other layer, and the other layer will decide if the final information is good or not. And the last layer is going to give the final result that is going to tell you if what you saw here is a circle, a square, or a triangle. And sorry, I forgot to say this, that all these input layers, in the case of we are trying to recognize an image, all these layers are going to be a pixel of each one of these image. So we have 784 pixels that are be organized in a vector. That is, you cannot see it quite well, but this is the final one. This is the 784 pixel. So you do this with a forward propagation. So you, at the end, you're going to have a result. We give them a circle, but the result that this network told us is that this is a circle, but a square with 50% of probability, which is incorrect. So how the algorithm will know, or how it could improve this result, is not just doing a forward propagation of the network, but it's also doing a back propagation of the network. So it will go back, and it will tell us which one of these neurons was more effective, and it will do it multiple times, like multiple times, to see which one was more effective, and also which weight can give to a specific neuron. And then it will do a combination of the activation functions and also the weights until we got the proper result. So at the end, they got the proper result. There's going to be a circle, and it will tell you which error we'll have in the circle. So it's going to be supposed to be a really small error. So why, how, or in which case these deep neural networks are useful, I'm going to take into account in this talk that they're going to be really useful for checking images. So you divide these images in different pixels, as what we did before, and then from we're going to organize in a vector of an input layer, and then we have this hidden layers. The output is going to give us, in this case, a bird. But there's like one issue with this, is that they say that this bird is not organized in this position, but they say that the bird is with the head down, and then it's like flying to the other way around. It's something really unusual, but it could be happening. And what if this thing happens? So what if the bird moves a little bit? Then we did with checking each pixel is not going to be useful, because we're not checking the pattern of how the bird can move, or if this bird is not in the position as we trained at the beginning. So this is, sorry, before this, why I'm taking into account images is because in particle physics, we also have images, or at LHC. So one of these examples are jets. So jets, they are different if they are a jet of any hadron. So a really energetic jet will have something like this. But let's say we want to have a tau jet, and the tau jet is different from the other ones because it's going to be more narrow. Then I have another example here of a B jet, and how the B jet, that is also really narrow, will distinguish from other jets. Here I put some light jets, but it could be also big jets like these ones. And in CMS, we have something like this. So this is a picture of CMS, and we have different type of jets, and we distinguish, we reconstruct some of those jets. And this is, as what you can see at the first sight, it's kind of like an image. So you can distinguish the different jets as how you distinguish a bird. But now comes the problem. Oh, no, not yet, sorry. And then, okay, how you distinguish a bird. So the nice things about deep neural network, that is the what I explained before, is that it's kind of like a hierarchy process. You go from the most basic things, like in the bird will be, let's try to check the eye, so the edge of the corner of the eye, so the edge of the corner of the figure, then you can reconstruct an eye, and then from the eye you can reconstruct the face or the shape of the bird. In the case of jets, it's something pretty similar. From the jets you can distinguish the hadrons, and then from the hadrons they are reconstructed by tracks and the cluster of the colorimeters. From this you can take the hits. Then at the end you can check the colorimeter cells from these color clusters. So now, as I was mentioning before, so of why the deep neural networks are not that useful if the if the bird is pointing backwards, or if the jet is not in the exact position that we train, then you will need to have a different method to check these changes on the image. So here you have kind of like this effect. So you have a filter. So let me explain again this. You can have different pixels, as I mentioned before. And what we can do is that we can introduce a new thing that is called a filter or a kernel. And what this kernel filter does is that it will move to the right, to upwards, to backwards, or downwards to see a pattern on this image. And then when it distinguishes a pattern on this image, it will give it to a neural network, and then from this you can take an output that it will be more precise than a normal deep neural network. So this filter could be useful for, so you can have just one filter, let's say a filter that can distinguish, I'm gonna put it there. So you can have one filter that could be really useful to distinguish corners of a face, or corners of the shape of a bird. So you can see here that this filter is really good for doing that. But you can have the filter for different things. Let's say, for example, that you have a filter that is going to be really good for checking the different color of the face, and you can have another filter that could be really good for checking sorry, I was unmuting Marcelo. So you can have different for colors, and you can have another one for, let's say, another kind of shapes. So here you can see an example of all the different filters that you can use. So you have a banana, and then you use one filter, and then you use another filter, let's say one filter for the color, another filter to distinguish the background. So how many filters you use is something that you can check here. So here I put, like, let's say that you have 3 different images at the same image, but in different colors, and you use 16 filters for this different image. And from these 16 filters, you can have a map of characters. And this map of characters are going to be a broad shape, or a broad, let's say, a broad book of different images that you can have from here, and you can choose which ones are more useful for you or not. So then you can have one neural network that are going to use these like images as input, and then this layer of neural network are going to use these filters, and then from these filters you're going to have then other filters that are going to use these filters as input. I'm sorry, maybe it was a little bit complicated, but the idea of this is that the first filter is the same thing as what we got from the DNN. We got the more basic filters, the more raw information filters, and then the output is going to be the input for another filter that's going to be more robust. Let's say that the first one's going to just check the edges of an image, and the other one's going to check maybe the eye of a person. So at the end, we have a shape that is very similar to this. So we're going to have input layers are the left. These input layers are going to go to hidden layers or hidden layers of filters that are going to be map of characters, in fact. So this map of characters are going to be reduced because we're going to have less pixels. We have big pixels for that ones, then we're going to reduce the pixels. We're going to concentrate in one area, but we're going to have more characters. And at the end, we're going to have like a single pixel with a lot of characters. These ones are going to go into a machine learning algorithm, DNN. And this DNN will tell us which filter is useful, which is not. And it will go backward because of the error that you can have from the truth information with the training information, and it will tell you which filter to use and at which stage. This is very important for different things at LHC. So I put like one example here. This is called the pileup mitigation with machine learning algorithm. This one uses CNN. So what we have, what is pileup first? So at LHC you have many. So at LHC you have collision of protons. So at the end you have many collision of protons. Some of the collisions are going to be useful, other ones are not. So the ones that are going to be useful are going to be safe, and the other ones should not be safe. So, but it's complicated to distinguish one from the other. So this algorithm is doing that. So you're going to have one collision that is going to be useful, that is in blue, and the idea is to try to separate all the other ones. How you separate all the other ones? You use different filters. One filter is going to be for low information, like low custody information. The other ones could be for electromagnetic information. And the idea is to distinguish your signal from all the patterns you can have. And you do this with different filters. And these ones are going to go to a convolutional neural network that's going to tell you which filter to use and which weight you can put to each one of these. And at the end, you're going to have as an output the event that you wanted to save. That is this like red one. This is also really useful for other experiments, not just the LHC, but I'm putting here the SNE, so it's a neutrino detector. And this one also uses CNN. Maybe it's more straightforward for this one because what this experiment does is that it takes picture of each event that they have as an output. So the idea is try to recognize which neutrino is an electron neutrino, mu neutrino, tau neutrino, just to look at the final state, because you can have a neutrino and also an electron. So the idea is to check which one is an electron, tau, or mu. And they do this by categorizing all these three different neutrinos, and they use a CNN because it's very well for images. And then I'm going to go to the last part of the presentation. Not going to talk again about CNNs, but another kind of machine learning algorithm, which is recurrent neural network, but I'm not going to go for the details, but tell you what it has been used. So there's a software that is called AI Feynman, which does symbolic regression to learn 100 equations from the Feynman of physics. And then what they do is that they use just any input parameter. They're going to give an output parameter, and the idea is to compare it with the actual equation, so the actual output that you can have from the equation of this lecture of physics book. They do it several times, of course. They do a recurrent network, and the idea, or the not the idea, but at the end, the output of this is that the prediction was the same value of what you can have from the equation. So you use a machine learning algorithm that learn this 100 equation from this book. So this is a paper that was published and everything, but something very similar. I didn't put a slide with that here because I didn't thought I was able to manage the time to get it. But the thing is that at the end, there's other people that are working on different aspects of recurrent neural network. And one of these was with lattice QCD. So with lattice QCD, they do something very similar. They train a recurrent neural network to reproduce the same result that they have right now. And for the moment, the precision is surprising that they have the same value of the prediction and also the target that we have with the normal lattice methods. So last thing I'm gonna talk about maybe the present and the future of machine learning, not just for physics, but maybe for many other ones. That is called the transformation neural network. So why this is very important? So I put here, the first paper was on 2017. So this was invented at the beginning to learn. So the idea was for this machine or for this algorithm to learn different languages and try to do a translation, just like Google Translate. But then it started to develop to do something different. To let's say that you begin like a phrase, and then it ends the phrase with something that could be related with how you begin it. So this was also used for a poem. Like you can start a poem and then it will continue with the poem with something else. And I put here an example of like I think it was also for the Star Wars movie. So you can see here the example of the Star Wars movie, that you start with something and then it will end with something that is important. Not. This was also used in biology with proteins. So you can also check the proteins, the structures, and you can also do a recurrent network that can tell us how the other proteins will integrate between each other. So after this, there's like a big, now it's a company, but it was a group of scientists before that's called OpenAI. Now it's also part of Microsoft because Microsoft kind of like bought this company. What this company did, it was using the same algorithm as before, the transformation. They did something that's called GPT. And GPT, the idea was to, again, for a machine learning algorithm to learn how to, with different words, how to write a letter or write anything that is related with what you put as an input. Let's say I put dear sir, and then it will say something about a letter. That is something you can see over here. So you just give like a first like an idea of what you're going to talk about, and then it will tell you how the letter can continue. I put there like 3 different GPTs. So the first one was 2019, and then the other one that was in 2020. Different is how many parameters you give as input. So the last one is the one that the people gave more parameters. That I believe that is like billions of parameters. Yes, it's billions of parameters. But the thing is that it's like the fun thing about this. Well, there are many fun things, but something that is really surprising about this one is that since many people were giving like computer algorithm, that they were giving coding as input to this machine learning algorithm, they give like, instead of giving just text, they also give like as an input a code. And then this algorithm took also these codes as inputs, and then it was also useful to kind of like write a code. So this is something that people were not expecting, but it did. The algorithm was also learning about how to do some coding because people input some coding in the middle. So this is how, at the end, for us that do a lot of code, this is how GitHub, that is one of the most common libraries to share code. This is how they invented something that is called the GitHub pilot. So what you do here is that you can define some, let's say, functions, and then you put as a comment what you want to do here. Let's say that you want to calculate, or you want to pass from Celsius to Fahrenheit. You put there, I want to pass Celsius to Fahrenheit, and then this machine learning algorithm that's based on GPT-3 will write a code that will do that. But it's really useful for us coders, and also could be also not useful because we can lose jobs because anyone can code now with this. Why this is important is because we didn't, like, our first intention was not to give code to this algorithm to learn how to code. We were just giving some words so it will learn how to write a letter or something like that. What is good is that you can use the same thing for, let's say, for example, the last thing that I mentioned, that it was Feynman AI. In Feynman AI, you give them some equations, or you give them some like facts, laws of physics, and it will give you like as an output some equations from these laws of physics. So what if we do the same thing, but we give like as much information as possible about quantum field theory, let's say. I put here, okay, about the standard model, and maybe, I don't know, supersymmetry, and maybe it will give us as an output something that is more useful, something that we didn't manage to understand before. And at the end, I'm gonna finish with this. This is a quote from Professor Schwartz from Harvard. So this is a professor who is he is doing theory, so he does mostly QFT, and also he does a lot of machine learning. So what he said at the end of one of his books is that I feel more optimistic about the possibility of transcendental progress in fundamental physics now than at any other time in my career, even if I myself may not be able to comprehend the final theory. So what he's mentioning here is that maybe the answer will come from machine learning. Maybe, and also he's very confident that maybe a machine learning algorithm can do something that it was not possible before. And also, even if we don't understand it, because we don't fully understand what machine learning does, but it can give you answers not just on experimental particle physics, but also in fundamental physics, or even more. So I believe that's the last slide. So any question?
Thanks, Seba. Thanks for the very nice talk. The gifts were amazing. I'm going to steal them from you at some point. Does anyone have any questions?
No, just to thank Sebastian. I mean, well, quite remarkable. Huh? The last quotation by Schwartz. So we have to wait now that physics will be done by computers, or I mean, from its own. I mean, without any instruction. That's the idea.
Exactly, but again, this is, we have to take this with gloves. Like maybe it's not gonna be exactly like that, but yeah, there's a big option that might be.
Okay, wonderful.
It's a kind of scary option, I would say. I don't know if I like it.
Yeah, I mean, machine learning can be scary. Like something that many people like might think that, okay, like we have like this thing that I called before GPT is very, very good. Then it can distinguish, let's say, cat from dogs very good. So let's try to have the same GPT to try to distinguish between frogs and, I don't know, lizards. And it will be really bad. It's not like the human brain. Like the human brain, the good thing about the human brain is that you can distinguish different things. So yes, like that's the optimistic thing that we can say about not machine learning. So the optimistic thing will be, okay, we need to train this thing for really specific things, really specific cases. Not optimistic cases like this one, that if we train it for, like, if we give like a lot of information as input, it could be trained for many things at the same time.
Yeah, I mean, if you see it from that sense, even the brain, the human brain, I mean, you from all your childhood, your brain learns to distinguish between a cat and a dog or a lizard, and so it's a long way. That's what I meant.
Okay, thanks a lot.
Sarah, just a question on machine learning and jets that you mentioned before. You mentioned that they were using convolutional neural networks for distinguishing jets, or just neural networks?
Yeah, I mean, for jets, they began with neural networks, and then they went to recurrent neural networks. But now there are most of the groups are using convolutional neural networks. I mean, at the end, what you would like is to see a jet as an image. That's why they're using this. Other people are trying to use graphos. So again, it's kind of like a image. So they're going that way now, not as before that they were using recurrent. That was, as you know, it's different.
And just to have the picture of my head, the actual image of the jet that they are giving as an input to the convolutional neural network, it's like a 2D projection of the jet, or is meant to be by layers of the sensors. I don't know.
Yeah. So yeah, it is like a 3D reconstruction. So the idea is to see the activity on the calorimeters. So if you see activity in a calorimeter, you can take kind of like a picture of the activity in the calorimeter. And from those, you can infer if it is a jet or not. So this is like, well, right now they're also reconstructing the track of the jet and the PT of the jet and all that. But something that we are pointing towards now is to don't reconstruct the track, but to just leave the picture of the activity in the calorimeter.
Okay, but I can imagine it's like a 3D matrix of painted or not pixels, let's say.
Exactly.
Like
Exactly.
Okay. And so you're trying to distinguish between like two clouds, let's say, or some
Exactly.
things that are kind of blurry. Okay.
Yeah.
Okay. Good. So is there any other question? I think not. Okay. So thanks, Seba, again for your very nice talk, and thanks for the people that came today as well. And we will see each other again next Thursday at 1 p.m. Bye to everyone.
Bye-bye.